PhD in Aerospace Engineering from IIT Bombay in 2006. Thereafter, he was admitted for his postdoctoral course in Turbo and Jet Engine Laboratory, Faculty of Aerospace Engineering, Technonian, Israel Institute of Technology in the year 2008. He has been associated with Faculty of Aerospace Engineering, Delft University of Technology, Netherlands, as an assistant professor from 2008 to 2014, and thereafter as an associate professor from 2014 onwards till date. His awards include NWO Visitor Grant 2010, Best Review Paper Award for the paper titled Infrared Signature Studies of Aerospace Vehicles, IIT Bombay 2009, Postdoctoral Fellowship, Israeli Ministry of Higher Education in 2005, and Best Research Scholar, IIT Bombay in 2004-2005. He is associated with International Society of Air Breathing Engine as a national representative and board member, member of Advisory Council for Aeronautics Research in Europe, WG3 Committee, that is Energy and Environment, member of International Gas Turbine Institute. He is a member of Dutch Gas Turbine Association. He is the member of the editorial board for international journals of turbo and jet engines. I would like to mention few of his present and past projects because his list of projects is quite big. So I'll be mentioning a few. Concept validation study for fuselage with filling propulsion investigation. Then combined cycle engines for aero engines, which is being partnered by NASA and ADL Stanford University. Novel aircraft configuration and scaled flight testing institution project, which is again partnered by Clean Sky, Airbus, and NCR. His publication list is again quite big. So his list of publication includes many research papers. So his publication overall citation is 1396, H index is 18, and I-10 index is 24. We are very much happy and pleased to have you today with us, Dr. Arvind. Now I request our principal, Dr. Abhijit Wadekar, to share his views. Sir.
Yes, am I audible?
Yes, sir.
Yes.
Yes, sir.
Yes, sir. Good afternoon, everybody. With the due respect to the ideals of Lord Buddha, Bodhisattva Bharat Ratna Dr. B.R. Ambedkar, the keynote speaker and our own member of the PS family, our alumni, Dr. Arvind Rao, Associate Professor, Delft University of Technology, Netherlands, Head of the Department, Dr. Pungle, Professor Prashant Pandit, all the faculty members, all the participants, and my dear friends. At the outset, it gives me an immense pleasure to say that our own alumni have come forward and accepted this invitation on behalf of myself and my institute, all the faculties. I extend my warm welcome to Dr. Arvind Rao, as well as thank him for accepting our invitation for this webinar on the topic, the aircraft propulsion. As every one of us know that the objective of the People's Education Society is to promote education, not only education, but to promote intellectual, moral, and social democracy. So, Dr. Arvind Rao is the product of PS, is a best example of an intellectual, the moral and the social commitment, how he has been again connected and accepted by accepting our proposal and educating our people, own people. So I once again thank him. Second, I congratulate to head of the department and his team for organizing such a good webinar and selecting such a nice topic. So again, Professor Pungle told in his webinar, in the introductory speech, that he wants to connect all the alumni and invite all the alumni in the webinar series and teach the students. It is a need of an hour. When we say that we want to make our students as well as the faculties also are required to be upgraded, we are required to know the outside world. So the COVID has taught us lot many things. It was not possible for Arvind to come to Aurangabad and share his views, experiences, and teach us. So this platform has helped us to connect. Arvind, the COVID has helped us, rather I would say, to connect Arvind and share his views with our people. So my dear friends, now this whole term is going to be online and we are required to take the maximum benefit of this. So I will not take much of the time. We are running already delayed this particular program. We were supposed to start at 2 o'clock, but because of some technical problems, the program has been delayed. I will not take much of the time. I once again wish all the participants, wish them a happy learning and wish every one of you a very good luck. And again, Pungle sir has wished me, because it is a very nice day for me. Today is my birthday, and Arvind is delivering his speech. And really, when he was there as a student, I used to call him as a scientist. Really, he has brought all my dreams come true. And really, he is a scientist. Every one of the participants who are there on this platform should patiently listen to him and be connected with him in forthcoming years. I am confident as and when we require any of the help from our alumni, they come forward and they're ready to help us. I also express my uh, willingness that Arvind should connect with this institute. He's very he has a very strong platform in the research. So there should be an contributory research works with the faculties. He should strengthen the research activity in his institute. Okay, so this is the uh, desire which I feel sincerely that he should come forward and collaborate with us as far as the research activity is concerned, so that students will get an hands-on experience to work on the live projects. Unless and until we don't work on the live projects, the students, we cannot say they will become employable. Things have changed. Engineering has become interdisciplinary. Any person can learn any of the subjects on the engineering. Those days have gone. Only the students from the computer science used to learn only about the software engineering. Now everyone has to be accept the change which has taken place in the industry. So it is the world of an automation, and we are required to know a lot many things. In addition to the core subjects, we are also required to know about the software engineering. We are required to know about the Python, machine learning, and whatnot, artificial intelligence. So, my dear friends, I once again thank you for the patient hearing and wish you a very happy learning. Thank you very, very much.
Thank you, sir, and wish you once again happy birthday. Now I request all the participants to fasten their seat belts, and I call our honorable guest speaker, Dr. Arvind Rao, sir, to share his valuable thoughts about the fundamentals of aircraft propulsion. Sir, over to you, sir.
Thank you. Thanks a lot for the nice introduction. And first of all, it's very nice to connect with you all. Once again, happy birthday, Wadekar Professor. And I also see some of the older faculty members who have joined. I saw Mr. Dobe as well as Mr. Tete. So good afternoon to you all. Uh, um, so as Professor Wadekar was mentioning, you see that COVID situation also gives us kind of opportunity, and that's how we can connect now. So what I'm going to do today is present to you the fundamentals of well, a very short introductory lecture on fundamentals of aircraft propulsion. Okay. Um, can you see my? Can you see the slides?
Yes, sir. Yes, sir. We can see.
Okay. Let me see if this works. What about now?
Yes, sir. We can see.
Yes, sir. It's
Okay.
visible.
Okay, great. Okay, so what I would suggest is that in case if you have any questions, what you could do is, of course, I will take questions at the end. But in case if you have any questions in between, you can always write your questions in the chat box, and I will try to answer as I go. Okay. So don't hesitate to ask questions. Don't be shy. There is nothing like stupid question. All questions are important. Um, and as Professor Vadikar was saying, I was from the first batch of PES, um, and so this is I have completed almost more than 20 years since we graduated. Okay, and it's good to see that things have moved on in Aurangabad. Okay, so let's get back to the topic. We are already behind schedule. Okay. So before I go to the crux of the lecture, I would like to give a very short introduction to TU Delft, the institute that I'm working on for the last 12 years. So TU Delft is located in the Netherlands. Netherlands is quite a small country actually in the north of Europe. Um, and this is the map of Europe, and you see that here is Netherlands. And Delft is a small town which is located between two big cities, The Hague and Rotterdam. And Delft is quite an old town. It has a history of approximately 1200 years old. Okay. And this is the view of the campus. This is the north side of our campus. And what you see, this is our library. This is the architecture building. This is mechanical engineering, electrical engineering, civil engineering, and so on. And aerospace is located on the south side of campus, which is not visible in this picture. So this is a view of our campus. Just to give you some brief data, or let's say information about TU Delft. It's quite an old university. Was founded in 1842, sorry, by King William II of the Netherlands. At the moment, we have what in India we call as departments. Here we call as faculties. So there are 8 faculties, which is like 8 big departments, with approximately around 15 bachelor programs and 30 master programs. And the total number of PhD candidates in the university is approximately 2,600. And in total, we have around 21,000 students on the campus, with around 80,000 alumni worldwide. And the total scientific staff, or the faculty members, is approximately around 2,000. So it's quite a big technical university. It's the biggest in the Netherlands. And just to give you some highlights from aerospace engineering, our Department of Aerospace was started in 1940. So actually during the Second World War. Um, and we have approximately 1,500 students in the bachelor program, and approximately around 1,300 students in the master's program. Okay, so by far we are the biggest faculty of aerospace in the Western world. Okay. Of course, apart from classroom teaching, we already have quite a good presence on online education, and that came very handy during the Corona crisis, because we could shift many of the things on online platforms very easily. We have approximately around 250 PhD candidates in our department, and around 130 faculty members. Okay. We are ranked 5th in the world this year. Yeah. And these are some of our facilities. So we do have a flight simulator. We do have, well, Delft has a very good history in terms of designing aircraft. So we still have some of the aircraft that was designed. We have a clean room, and this clean room is used to make satellites. We have currently two satellites orbiting around the world that were made here in Delft. We also have a micro aerial vehicle lab, and the vehicle lab is quite famous. Recently, it got 1 million award from Lockheed Martin for a competition. We have a scale flight lab where we do small scale flights to actually test them. We also have an aircraft, Cessna Citation, which we use for teaching as well as for research. We do have wind tunnels, a large number of them, actually around 11 wind tunnels. So wind tunnels where we have flow speed from 30 meters per second to all the way to 8 kilometers per second. So hypersonic velocities. Of course, we have manufacturing lab and also a combustion lab where I am more active in. Okay, so let's go to the topic and let's talk about the first flight. Okay. Again, if you have any questions, please do not hesitate to put it in the chat box. Yeah. So the first flight, I mean, flying is always has been a dream. And whenever we see birds, we think, wow, I mean, they can fly, and can we do that as well, right? I mean, I would like to ask you a question. You don't have to answer now, but think for yourself. And would we fly if there were no birds in the world? That's, of course, a kind of philosophical question. But think about it. Okay. Now, when you look in terms of the early attempts of flying, of course, people thought the best way to fly is to imitate birds. Yeah. And there are some videos that I'm going to show you. And that's how sort of people try to fly. Okay. So. Yeah. Okay. And so this happened, right? In this case, of course, the person is just jumping off a rock, but in many cases they jump off from cliffs, and many people actually ended up losing their lives. Yeah. Now, of course, very soon we understood that our systems of muscles is not capable to generate enough power to provide a lift. Yeah. And so the idea of having a machine to do that came early on. Yeah. So there are some other examples. Okay. So here you already see a kind of a machine where there is some kind of a wing, yeah, and there is some kind of a propulsion system, not very elegant, but nevertheless, these were the early days of aviation, and people were trying all kinds of things. Yeah. So let's go here and see. Yeah. So you see that a large number of attempts were actually carried out, and not many of them were successful. Okay. But over a period of time, of course, the thinking evolved, and people learned from their mistakes. And well, there were some other crazy ideas as well, like, for example, so the name of this machine was Sky Car, but it did not take off from the ground. So again, there were many more attempts. Now, one of the first persons to actually sort of formalize this discipline, in a sense, was Sir George Cayley, and so he was one of the first ones to actually apply scientific methods to study flight, to study the lift that is produced, and so on and so forth. And he's sort of considered the father of aviation, in a sense. And one of the important things that he sort of pointed out is that powered flight would be possible if an engine would be able to produce more power in proportion to its weight. Yeah. So he coined this term that we now refer to as power to weight ratio. Yeah. And that's very, very critical. So he understood the importance of weight and the importance of power. And he also understood that if you want to take off from the ground, then you have to produce a lot of power without weighing too much. Yeah. So he was one of the first ones to formalize many of these concepts that we take for granted today. Um, of course, you know this picture, I think. Yeah. This is from the first flight. Yeah. From 1903, from the Wright brothers. Now, if you can use chat function, then could you sort of tell me what was special about this flight? We call it first flight, but what was first about it? Anyone? Okay, so the first thing about this flight was that it was a powered flight. Yeah, it was heavier than air flight. Yeah, it was a controlled flight. Okay, so for example, hot air balloons were existing before this, okay? But they were not heavier than air. Hot air balloon is created because uh, that hot air has lower density and it creates its own lift. Okay, so it's lighter than air, and of course, hot air balloons cannot be controlled. So you are always at the mercy of the winds, and you go where the winds take you. Okay, so this was the first manned, powered, controlled, and heavier than air flight. Yeah, and that's why this is called as the first flight. So when you look at this first flight, which happened in 1903, 17th of December, in Kitty Hawk Beach in Ohio, and what you see is that the first flight was actually not much. It was only 120 feet and lasted 12 seconds. I mean, this is, when you consider 120 feet, this is actually less as compared to the wingspan of a Boeing 747. So in terms of span, it was not much, but it still created history at that point. And of course, they had several more tests on that day, and in the last flight on that day, they also crashed. But you already see that they achieved quite a remarkable distance, actually, more than 800 feet, and almost flying for a minute. Yeah. So you already see that there were quite some improvements. Um, Now let's see how did things evolve as we went along. Okay. So one of the main things that was key for Wright brothers. I mean, apart from the fact that they had to design this biplane and they had to also design their own propellers and so on. But one of the key things that enabled them to do this is actually the IC engine, right? So IC engine was the best power to weight ratio available at that time. I mean, if you look at this engine, which from today's standards is quite rudimentary, but it weighed around 90 kilograms and produced around 12 horsepower. Now, 12 horsepower is not much, right? I mean, most of you use I'm sure you must be using bikes or something or cars, and then they have much more power than this. Okay, but for that time, this was quite a state of the art. Um, and remember that this was still an uncooled engine, so they could not use this engine for a long time. Now, so the propulsion system was sort of one of the key factors in enabling them to provide enough power without having to weigh a lot. Okay. And before this, actually, there were also other attempts by other people where they tried to use something like a steam engine, but steam engine was extremely heavy. Um, so you see that the progress in science always happens over a period of time, and a large number of people are involved. And that's why it is important that in the scientific community you always share your understanding, because people don't have to repeat the mistakes that someone else has done. Right? And that's why we have all these journal papers where we sort of disseminate our knowledge. Okay. So let's take a kind of a change the gear. So we talked about the first flight. So that was approximately 117 years back, and let's look at how things have progressed. And when you look at aviation, the progress was really in the early years was fantastic. I mean, after Second World War, there was a huge change in civil aviation. So in terms of distance, you saw that the first flight was only 853 feet, And so today, you would take a super jumbo like A380, a beautiful aircraft. Airbus stopped producing this, but I think this is a very elegant aircraft, huge, 550 tons takeoff weight, and in a single class seating capacity, it can go up to almost 800 passengers. So you can take 800 passengers all the way to around 14, 15,000 kilometers. Yeah, so that's the kind of the distance that an aircraft can cover today. In fact, the next generation of 777X and also A350 long range A350,000, they can go almost around 18,000 kilometers or so. Yeah, so it shows you how much what has been the progress made. In terms of payload, well, the first flight could carry only Wilbur Wright as the payload, yeah, one person. But then you see this huge monster that is called as Antonov 225. It's a fantastic and beautiful aircraft. Um, it has a payload of 250 tons. Yeah, it was designed for the Russian space program, but it has been used all over the places for all kinds of things. And it's still one of the most reliable ways to transfer any heavy material in a short period of time. Now, um, and and you see, of course, these huge turbofan engines, six of them. Yeah, but one of the interesting features that I find, apart from the engines and the aircraft, of course, every feature of this aircraft is beautiful. But one of the most intriguing feature of this aircraft, which I find, are the landing gears. Yeah, so when you look at this landing gear, I mean, it's huge. Um, it's sort of mind-boggling to see there are so many landing gears for such an aircraft. Okay, in terms of speed, yeah, so in terms of speed, of course, you see that Wright brothers, the first flight was something like 20 feet per second or something in that order, whereas, of course, there was Concorde aircraft, which unfortunately does not fly anymore, but Concorde already broke the speed for civil aviation. Yeah, it was flying at around Mach 2.2. That means 2.2 times the speed of sound at around 18 kilometers altitude. So in fact, you could take off from Paris and you could land in New York. And if you take off from Paris at let's say 8 o'clock in the morning, you would land in New York before it becomes 8 in the morning in New York. So you could sort of cheat the time a bit um, in a sense. Yeah. So that was a fantastic aircraft, but unfortunately commercially not successful. Yeah, and that's well, there are several reasons for it, but one of the main thing is that of course when you fly supersonic, um, the amount of fuel consumption is extremely high. Yeah. And of course there are environmental problems and well as noise problems. Okay, so now we have looked at the progress that has been made. Um, so let's look at some of the basic principles of propulsion. Yeah. So I'm starting at a very basic level. Yeah. So how do you propel things? So one way is to take a balloon. Yeah, we have all done this. We have played as children where we took a balloon, we sort of blew air in it, and then we let it go, and then it just goes randomly everywhere. Okay, and that's what happens, right? But when you think of it, there is a propulsion principle here. So the pressure inside the balloon is high, the pressure outside in the atmosphere is lower than what is inside, and because of the pressure difference, the air actually comes out. Okay, and as it comes out, it accelerates, right? And so that means that this jet velocity is high. Okay, so there is a change in the momentum of the momentum of the air which was inside, yeah, as compared to this, and this change of momentum produces force, and that was Newton's second law of motion, right? And because every force has an equal and opposite reaction, so you get the thrust. Okay, so from a principle point of view, it is pretty easy. Okay, the other toy that most of us we have used as kids is this kind of this Chinese propeller where you just rotate it and it just goes around, yeah, and it goes up. Again, the principle is the same. You see that it cuts the air and it accelerates the air, it pushes the air down, and in that process, it sort of creates an upward force. Okay. So this is the basic principle of propulsion, that you change the momentum of the fluid. Okay, and in most of the case, it is air. For aircraft, of course, it is air, and for rockets, it's because rocket has to operate in environment where air is not available, so it can use another fluid. Okay, so that's why rocket has to carry the oxygen as well as the propellants both. Yeah, whereas in an aircraft, you don't have to do that. We always use the ambient air. Okay, so if this is the main principle of propulsion, let's say, then what can you do? So again, let's take this balloon as an example, right? I mean, of course, when you do a balloon, it will go only a few meters, and that's it. But if you want to sustain this balloon for a longer time, then maybe you have to connect it with kind of a compressed air, yeah, so that with a pipe where this pipe is now sort of giving continuous pressurized air to this balloon, and then it's coming out, yeah, and in that process, then the balloon you will hopefully will go a bit longer. But it's not a smart thing to do, right? I mean, you always need some kind of a connection and so on. But okay, one slight improvement over this concept would be if you sort of have a kind of a compressor in the balloon itself. Yeah, theoretically, hypothetically, you can have it, a small compressor in the balloon, and then that compressor is rotated by a motor, and this motor is then given by electricity, right? I mean, well, if you don't want this electrical wire and so on, you can have some kind of a batteries. Okay, so that's also can be done. Now, but again, the energy that you can carry in a battery or so on is limited. So other thing that is actually you can do is instead of providing a compressed air, yeah, what if we can generate this high pressure gas within the balloon itself? Okay, and you can do that by having multiple stages of compressor. Yeah, you can pressurize the air, but how is the compressor driven? The compressor is actually driven by a turbine. Here, what you see in red. Now, of course, but this cannot happen in a perpetual way, right? Because the power that is produced by turbine is not equal to that of the compressor if you do not add additional energy into it. Okay, so in order to sustain the process, you have to have additional energy input to this compressed air, and that is done by a combustion chamber. So what is done is you have a compressor where the air goes in, yeah, it increases in pressure. You add fuel to this compressed air, you burn it. So at the end of the combustion chamber, you not only have a high pressure air, but you also have a high pressure and high temperature air. Now the turbine, at the end of the combustion chamber, extracts power from this high pressure, high temperature air. But even after the turbine has extracted the power required for running this compressor, there is still uh, um, a part of the power left, and that part of the power which is left is then can be used for propulsion. Okay, so this is in a very basic and schematic way. Yeah, you can visualize this. Okay, of course you can do it in a different way. You can also add a propeller and so on. Yeah, um, but nevertheless, this is sort of the basic principle of a jet engine. Okay, so what you see in a beautiful aircraft like this, Airbus A350, okay, or any other aircraft for that matter, yeah. So what you see is that the engines are hanging in here. So what they do is they take in this air, yeah, and they accelerate at a much higher velocity. And in that process, of course, they change the momentum of the air, and that's what creates force and thrust. Okay. And inside this, there is a fan, there is a compressor, there is a turbine, there is combustion chamber. So these are the main elements that I showed you in the earlier picture. Okay. So if you look at an engine in a bit more detail, so this is how it works. So this is what is called as a turbojet engine. So most of the modern aircraft, like this one, they use what is called as a turbofan engine. Okay. So there are several differences between turbojet and turbofan, but in the view of time today, it's not possible to go into the details, okay? But nevertheless, the basic principle is still that you change the momentum of the air, okay? So in a turbojet engine, what you see is that there is this intake where air is coming. You have several stages of compressor, and you can imagine these compressors as some sort of fan, okay? So with every stage of fan, the pressure is increasing, okay? And that's why the density increases, and that's why you have to reduce the area, okay? So you see that the pressure would increase as you go downstream. Yeah. At this point, after the compressor, the air is at higher pressure, is at higher density. Okay. And of course, because of the compression process, it is also at a higher temperature. Okay. So what you can do is after this compressor, we can have a combustion chamber where we add fuel and burn. Okay. So that's at the end of the compressor. At the end of the combustion chamber, we have a high pressure and high temperature air, and part of that energy in the gases is extracted by this set of turbines which drive these set of compressors, and rest of the energy is what we can use for propulsion. Okay, so you see there are these 5-6 main components, and that is air inlet, compressor, combustion chamber, yeah, turbine, and exhaust. Okay, so in that sense, it's not a very complicated process. Okay, um, well, at least for the mechanical engineering students, you must have learned about the TS diagrams, and they are very, very important actually. So even in my lectures, I mean, I use TS diagram all the time, and with just by using TS diagram, you can actually do a lot of calculations, and you can also explain a lot of phenomena. Okay, so of course you see that these are two isobaric lines on a TS diagram. Yeah, and what you see is if you have an inlet here, okay, in the inlet there is nothing much happening. So it's an isentropic inlet. Okay, so there's nothing much happening. Of course, in a cruise flight, the total the static pressure would increase. Okay, um, but the total pressure will not. Yeah. So if we consider it as an ideal inlet, yeah, then more or less this would what would happen. And then you have a compressor. Okay, the compressor would increase the pressure as well as temperature. So you see that this uh, the, the the solid line is at a higher pressure and the dotted line is at a lower pressure. Okay, and assuming isentropic compression in an ideal case, yeah, your point 3 would be here. Okay, and of course then you would add fuel, and the combustion chamber is a constant pressure combustion chamber, so that means that it would increase the temperature, but the pressure would remain the same, so it would go from on this isobaric line, yeah, upwards. Of course, the entropy would increase, so your point 4, which is at the end of the combustion chamber, is somewhere here, and then from 4 to 5 you have an isentropic expansion. Okay, so this line should be equal to this line in an ideal case. Okay, so the turbine is driving the compressor, and then the remaining power can be used for whatever purposes. Okay, so in case of a jet engine, of course, it is used for creating thrust, whereas in an industrial gas turbines, you can add more turbine stages, and then you can connect it to a generator. You can produce power. Um, you can also connect more turbine stages and then connect it to a rotor, like in a helicopter engine, or to a propeller, like in a turboprop engine. So you can do all kinds of things. Yeah, but the basic working principle is still what is called as the Brayton or the Joule cycle. Okay. Now, if you compare a gas turbine with an internal combustion engine, which you must have studied in your bachelor's, yeah, so the processes are not very different. It's still more or less the same. You have an intake, yeah, you have a compression, you have combustion, and then you have exhaust. Okay, but the main difference is that first of all that an IC engine, in that sense, is an intermittent cycle. So you have one power stroke in a four-stroke engine. Of course, you have one power stroke in four strokes, whereas in a gas turbine engine, so this is a continuous cycle. Yeah, and that's why the specific power output of a gas turbine is extremely high as compared to that of an internal combustion engine here, or a reciprocating engine, to be more precise. Okay, so a reciprocating engine, it has its own advantages, but it also has its own limitations. Whereas when you look at something like a gas turbine cycle, it is a continuous cycle, and specific power output can be much higher, and also the efficiency can be much higher if the operating pressure ratio is high. Okay. So let's see how powerful is a gas turbine. Yeah. Now, just for the sake of simplicity, well, if you have a fancy car, yeah, then you typically have around 150 200 kilowatts of power. Okay, and if you have even more fancy car, so people who don't know what to do with their money and are mentally not grown up, so they buy these kind of fancy cars like Ferrari, yeah. And well, you can see you can have around 500 400 kilowatts of power. Okay, but then if you look at one engine um, of something like 747, okay, then you have approximately around 30,000 kilowatts of power that is produced. Yeah. So you see the difference in the magnitude of the power. So that means that one turbofan engine, yeah, is almost equal to around 80 Ferrari engines. Okay, and remember that at full takeoff thrust, your aircraft has a bigger aircraft like A380 or let's say 747. They have four of these engines. So that's why you can accelerate from standstill to around 250 kilometers per hour in such a short distance in such a short time, and then you can take off. So so this high amount of power is something that is a specialty of gas turbine, okay? And that's why we use these in aircraft. Uh, Again, if you have any questions so far, please put them in the chat box and I will answer them. Okay. Uh, Up till now, at least I don't see any questions. Okay, so let's look at the propulsion system in a different way. Okay, so what are the main elements of an aircraft propulsion system? So first of all is that there are three main elements. Okay, first is that energy source. So you have to carry an energy source on board an aircraft, okay, which will provide the energy. Now this you have to convert this energy into work, okay, and this work then has to be converted into thrust. And of course, you have to do this all, sorry, and you have to do this all in conjunction with the aircraft and its mission. Okay, and what do I mean by this? I'll give you some examples. So, for example, in terms of energy source, in terms of the thrust converter, right? We already saw these examples. So we could either use a kind of a propeller, or if we could use a nozzle to create thrust. Okay, so we already looked at that. Okay, so this part is covered. In terms of the energy source, okay, um, we could use different energy sources. So for the students who are out there, maybe you can write some of the energy sources that you can use for aircraft in the chat box. What do you think are the different types of energy sources that we can use for aircraft propulsion? And it can be small aircraft, big aircraft, or something else. So don't be shy. I don't see any messages. Is there a problem with the chat box or?
They are blocked.
Sorry?
They are blocked.
The chat is blocked?
Yes.
Oh, okay. I'm sorry to hear that. But you could also say, actually, that's not a problem. Okay, so of course, Dr. Pungle said that we can use solar energy. Yeah, so the solar energy you can do that. You have to use solar cells, and but the amount of solar energy which is coming on an aircraft is much less. But there was one attempt, what was called as solar impulse. So it was a Swiss team that designed an extremely light aircraft with a very long wingspan. So the wingspan of that solar impulse was much longer than that of 747 aircraft, and so it could generate, let's say, sufficient power to just for one person to take off and fly at a very low speed. Yeah. So solar energy can be used for also for unmanned aerial vehicles to some extent in order to sort of charge the batteries or at least to extend the life of the batteries. But for commercial aviation, solar energy cannot be used. Yeah. So what is used typically? Yeah, so of course batteries, you can charge batteries, and this is always used for drones. Yeah, and one of the characteristics that is used to characterize the energy sources is to see how much amount of energy can you store per kilogram of that energy source. Yeah, so energy density. Okay, so when you look at a battery, say for example some nickel cadmium battery, of course there is always a range, but these are some typical values that I'm mentioning here. Yeah. So it's approximately around 0.14, 0.15 megajoules per kilogram. Okay, so not much. Yeah. But if you take something like lithium-ion batteries, then you can go up to almost 1 megajoule per kilogram. Okay. Um, so you see that the energy density is already better for lithium-ion batteries. Yeah. Of course, there are some experimental batteries like lithium sulfur and metal air batteries where uh, at least the hope is that the energy density can go up to around 2 or 3 megajoules per kilogram. But when you look at kerosene that is typically used in aircraft, yeah, so you see that it's approximately around 43 megajoules per kilogram. So it's a kerosene is a very energy dense fuel. It is similar to diesel, by the way. So that's why um, it an aircraft can go to a very long distance because of this energy density. Yeah. Of course, you could also think of hydrogen. Yeah, hydrogen also has very high energy density, but it also requires more volume. And so if you want to carry hydrogen in an aircraft, of course, you have to do it in a liquefied form, liquid hydrogen. And then liquid hydrogen has to be stored at under very cold temperatures. And that means that you cannot store it in the wings, and you have to store it in the fuselage. I'll give you some examples of this later on. Yeah. And that is a problem with hydrogen. Well, believe it or not, but after the Second World War, in the 50s, actually, in the late 40s, in the 50s, in fact, there were serious attempts of using uh, uranium, or let's say a nuclear-powered aircraft, both in US as well as in Russia. Um, and of course, you see nuclear-powered submarines, nuclear-powered ships. So when you take something like an aircraft carrier, yeah, many of these aircraft carriers, they tend to be nuclear powered, so you can use these aircraft carriers for years, so approximately 15 years without refueling. Yeah. Of course, the problem with nuclear power on board an aircraft is that the weight of the shielding is extremely high, and of course, in case of an unlikely scenario of a crash or something, then there's a huge danger of radiation leakage. Yeah. So that's why this is ruled out. But in principle, you can use different kinds of energy sources. Okay. Of course, you also have to convert this energy into work, yeah, to drive the propeller or to produce hot gases, which can then be used from the nozzle. Okay. So when you look at different examples, of course, you talk about, let's say, IC engine, internal combustion engine, reciprocating engine. When you look at some of these engines, at least the state of the art that are used for high performance cars, yeah, then you have approximately 1 kilowatt per kilogram, yeah, maybe a bit more. And of course, if you use electrical motors, then they're approximately 5 kilowatt per kilogram. If you use Wankel engines, then they are around 2.5 kilowatt per kilogram. But if you use a gas turbine, then approximately it's around 10 kilowatts or even more per kilogram. Yeah. So you see that why a gas turbine is used, because it has not only, I mean, it has extremely high power density. Yeah. Um, so in a sense, you can use different types of energy sources, what you see on the left here, yeah, with different kinds of energy converters in the middle, and different form of thrust producers. Okay. So for example, for an drone, what is typically done is, of course, you would use something like a battery with an electric motor with a propeller. Okay. Of course, as and when different kinds of batteries are available, you can use different kinds of batteries, yeah, with electrical motors and propeller. Okay. You could also use the gasoline and a Wankel engine and a propeller. Okay, or you could use hydrogen with gas turbine and a propeller, or hydrogen with gas turbine with a nozzle. Yeah, so you can use different permutations and combinations depending on the aircraft type and the mission requirements. Okay. Um, okay, so let's look at the fuel burn. So what this graph shows you is the increase in the efficiency of um, aircraft over the period of time. Okay, so on the left axis, what you see is, let's say, in a non-dimensionalized way, um, the amount of fuel consumption per passenger per kilometer, yeah, over the years. And what all these blue dots you see are the different aircraft types. Okay, so as compared to the earlier jet engines in the late 50s and the early 60s, so when you look at state of the art, let's say A350, for example, then the fuel consumption is approximately 75% less. Okay, and that is also one of the reasons why over a period of time, aircraft tickets have become much cheaper. I mean, more and more people in the world fly today than ever before. Of course, I'm talking about pre-corona times. Yeah, and flying through in an aircraft is not so expensive anymore. And one of the main reasons is because of the decrease in the fuel consumption, because fuel cost is one of the main costs for an airline. Okay, and these red dots that you see are the engine fuel consumption. Okay, so of course, if the engine fuel consumption reduces, then the aircraft efficiency increases quite a lot. Also because the aircraft not only has to carry less fuel, but also because it has to carry less fuel, then it can be lighter and so on and so forth. So there is a kind of a snowball effect. Okay, so engines have become much more efficient, and that means that the aircraft also has become more efficient. Of course, there are other things as well. For example, the aerodynamics of the aircraft has improved, the structural weight has reduced, um, so on. Okay. Okay. So we covered a bit about the history, a bit about the basics of propulsion, and then the question is, what can we expect for the future? Okay. So let's take a look at that. Now, one of the things what you see is, sorry, one of the things is, as we were talking about, is because more and more people are traveling. Okay, so you see more and more aircraft going in the air at any point of time. Yeah. So pre-corona times, um, so there are around 25,000 aircraft in the air, yeah, being used worldwide. And what you see here is the increase in the passenger numbers. So right from the let's say early 70s, yeah, to now. So this is so approximately around 4.5 billion people or passengers, yeah, traveled through air in late 2019 or early to 2020 before Corona crisis happened. And it is expected. I mean, the air traffic is growing at around 4-5% every year. Of course, it depends from region to region. For example, in India, it grew at in double digits, 12%, 13%, 15%. Whereas in Europe and so on, because of we are already at a developed stage, so the growth was not as much. Okay, but still, when you look at the worldwide average, it has grown over more than 5% over the last 10, 15 years. Okay, so which means that the air traffic actually doubles every 15 years. Yeah, and so that is a huge challenge, of course, and that's why there are longer lines in airport and so on and so forth. Okay. So what you see here in this graph is, and this is coming from our own book. Now what you see here is the number of passenger kilometers traveled by different modes of transport. Okay, so the black represents automobiles, the gray is buses, and then you have the light gray, which is rails, and the yellow is aircraft. And of course, in the 60s, hardly anyone traveled with air traffic. But coming today, well, incidentally, in this year, we used 2020 as a baseline, and but nevertheless, if Corona wouldn't have happened, so we would have gone here. Okay, so we already see that a large number of passenger kilometers is actually covered by aircraft, and by 2050, so air travel will be as much as road travel. Of course, what you see is that in road travel, electric batteries are coming into, and electric vehicles are coming into. and not so much in India, but in rest of the world. If you look at China, for example, a large, around half a percent, I think approximately around 50% of all the new cars that were sold, a large majority of them were electric cars. Okay, so this is very good for from a local environment perspective. Of course, you also have to take into account how the electricity is generated from. If the electricity is generated from a coal-fired power plant, then it's not good. But if the electricity is generated from a wind turbine or using solar energy, then it is good. Okay. But coming back to aviation, you see that it is projected that because of the increase in the growth um, of aviation, so in terms of passenger kilometer, yeah, aviation would be as much as road transport, which means that the emissions from aviation will actually surpass all other emissions. Okay, and that is quite a big challenge. Okay, already people who live around airport and so on, they complain a lot about pollution, about emissions, about noise, and so on. So that has to reduce. Okay, so when you look in terms of emissions that come out from an aircraft, of course, it's burning kerosene, so there are emissions. And apart from water vapor and CO2, which is the product of any hydrocarbon combustion, so you also have NOx, which is called as NO, NO2, yeah, and then there you have sulfur dioxide, you have carbon monoxide, you have unburned hydrocarbons, and you have soot. So all these emissions, they have different impacts. So at the ground level, of course, near the airport, they have a different impact. But when the aircraft is cruising at 10 or 11 kilometers altitude, then it has quite a big impact on the global warming. Okay, so these are the things that have to be reduced. So around up till around 1,000 meters, let's say around a kilometer, of course, the local air quality is changed because of aircraft. But when it is flying at around 10, 11 kilometers altitude, then it changes the climate. Yeah. So there are, of course, and these are for military aviation, but I mean, from a volume point of view, it is not so much as compared to civil aviation. Okay, so now at least in Europe and also in US, so there is this advisory committee for aeronautics research in Europe, and the aim is that how will aviation grow in the coming years, and the idea, or at least the goal, is that for an aircraft, let's say for a new aircraft in 2050, the aim is to reduce the CO2 emission by approximately around 75% as compared to an aircraft in 2000. Okay, and the NOx emission by around 90% as compared to an aircraft in 2000, and the noise emission by around 65% as compared to an aircraft in 2000. Okay, so, and these are extremely ambitious goals, and this is where, let's say, Europe and as well as the European Commission is putting a lot of emphasis on and money in terms of making sure that our aircraft become more sustainable. Okay. So there's a huge political drive also to reduce emissions from aviation. And one, of course, you see, we have to make the engines better. We have to improve the aerodynamics. We have to reduce the structural weight. But one way to reduce the emissions from aircraft is also to look at different energy sources. Yeah. So, of course, when we talk about energy sources, again, coming back to mass energy density, this is one of the main criteria. Yeah. And the other criteria is what is called as the volumetric energy density. Okay. Well, I see a question here from Dr. Pungle, and that is, can different layers affect the performance of the aircraft? I think, do you mean different atmospheric layers? And if that is the case, then yes, I mean, and a normal civil aviation
atmospheric layers.
Okay, yeah, thanks. So a normal aircraft is always designed to go around in the edge of troposphere. So we have the troposphere, and then what is called as the tropopause, and then you have the stratosphere in the atmosphere. Yeah, and typically that occurs at an altitude of around 10, 11 kilometers. Yeah, so the temperature reduces as you go up above in the troposphere at around 6.5 degrees per kilometer. Yeah, And the weather phenomena that we all experience it happens at much lower altitude. So typically, the aircraft is flying above the weather. Okay, so it's flying at around 10, 11 kilometers altitude. Now the air pressure at that ambient at that altitude is pretty low actually. So the air pressure is approximately one fifth of one fourth to one fifth of what you experience on the ground. Yeah, which means that the air cabin has to be pressurized. Okay, and the temperature outside is typically around minus 40, minus 50 degrees, which means that the air conditioning system has to account not only for the pressure but also for the temperature. Yeah, and you have to have a lot of insulation, otherwise we would all freeze inside an aircraft. Okay, uh, so yes, so that is in terms of the aircraft design, let's say. But the advantage is that we are flying above the weather, um, and the fuel consumption of the aircraft also reduces because the air density is quite low. It's less than half of what is at atmosphere, so the drag of the aircraft reduces quite a lot. Okay, so then aircraft is typically designed to cruise at around 10, 11 kilometers altitude. Um, Most of the civil aviation aircraft. Of course, business aircraft they go a bit higher. So business aircraft, jet aircraft, they are typically going at around 12, 13 kilometers altitude. Turboprop aircraft they go at much lower altitude, approximately around 5, 6 kilometers, but they also go much slower. Yeah. So even when you look at the airspace, there are actually highways. Yeah, and these highways are differentiated with respect to the speed of the jet of the aircraft. So turboprop aircraft are typically slow, so you cannot put them in the same um, line with jet engines, because then you will create all kinds of traffic jams and so on, and you don't want any crashes there. Yeah, so turboprop aircraft they go at a much lower altitude, and turbo fan or turbojet aircraft they go at a higher altitude. The military aircraft they can go at a much higher altitude as well. Typically military aircraft they go supersonic, and in order to fly supersonic you really have to go higher, because then the air density is lower and then the drag reduces further. But anyway, so they can go up to 18, 19 kilometers or 20 kilometers in altitude. Yeah. So I mean, a military aircraft in that sense is much more difficult to be designed. Um, yeah. Okay. So of course, so the different layers of atmosphere they have quite a big influence in terms of their performance. Okay. Now coming back to energy source, so you see that for example kerosene is here. Yeah. Well, incidentally, fat metabolism is also here. Methanol is here. You see, batteries are here. So batteries are pretty poor in terms of energy density, both volumetric as well as mass energy density. Now, LNG is something interesting. LNG is liquefied natural gas. So natural gas has quite high energy density, but very low volumetric energy density. So which means that you require large volume to store natural gas, and that's why natural gas is either always compressed or liquefied. And if you liquefy it, then the energy density increases quite a lot. Okay. Uh, and when you look at hydrogen again, hydrogen has a very high energy density, 120 megajoules per kilogram. So that's approximately 3 times more energy dense as compared to kerosene. So that's very good, which means that you, in terms of mass, you don't have to carry a lot of hydrogen. But the problem is that even when you liquefy hydrogen, the volumetric energy density is lower, which means that the volume of the aircraft will increase. Okay, so these are some of the trade-off criteria which we have to always take into account whenever we design the propulsion system as well as the aircraft. And one of the main things that we have to keep in mind is that if the mass of the aircraft increases for some reason, yeah, either it is because of the poor structure or is because of the additional mass of the fuel or something and so on. So then that means that because of the mass increases, then the lift of the aircraft has to increase, and because the lift increases, the drag of the aircraft increases as well. Okay, which means that the thrust produced by the engines they have to increase, and if the thrust produced by the engine has to increase, that means that the amount of energy that they consume also increases, and that means that the fuel weight increases as well. So when you look at a big aircraft, let's say for example A380, for example, on a long range mission, then the amount of fuel is approximately 200 tons. Yeah, that's huge. Okay, even when you look at 737 or A320 kind of an aircraft, which goes on a 2,000 kilometer range. Yeah, the amount of fuel that is required is around 8-9 tons. Okay, so you see that you know the amount of fuel that is carried on by an aircraft is actually sometimes even more as compared to the payload weight, which means that the passengers and the luggage and the payload and so on. Okay, so the fuel weight cannot be neglected at all. In a car, it's a different case, right? So in a car is typically around 40-50 liter tank. Yeah, and the weight of the fuel and the tank is not, you know, it's sort of negligible as compared to the weight that of the car or the weight of the passengers. But in an aircraft, it is completely different. Now, just for the fun of it, I put here sugar. Sugar has also very high calories. So, in case if you want to reduce weight, then avoid sugar. Okay. Well, we also have to keep in mind that if we start using other fuels, then they might be expensive as compared to kerosene. Okay. Now, what are we looking at actually? Most of the projects that we are doing are in conjunction with Airbus or European Commission. Yeah, and we are looking at ways in terms of how to make aircraft more efficient and less polluting. Okay, so how to make them sustainable. And this is one example where how we are looking. I mean, we are looking at, let's say, hybrid electric systems as well to see if we can use electric motors to boost the power of the engine at some phases, so that we can design it for a better operating point, and that is during the cruise. So we have looked at hybrid electric systems where we have looked at, let's say, incorporation of electric motors within a gas turbine in order for the electric motor to boost. And also for taxiing and so on, we can use only motors instead of engines, so that can reduce a lot of local air pollution. So these are some of the concepts that we have looked at. I have also mentioned some of the publications. Yeah, we are also active in another European project along with Airbus and Bauhaus Luftfahrt from Germany, and some other universities. So where we are looking at again a hybrid electric architecture where we use a very um, interesting technology, what is called as boundary layer ingestion. I do not have the time to go inside to the details of this technology, but nevertheless, this is a very interesting technology in terms of how we can integrate engines as well as aircraft, and we are using hybrid engine, hybrid electric architecture to see if we can design, let's say, a future um, twin aisle aircraft using this technology. And uh, yeah, so this project is almost ending now. Okay, so this is a schematic of the aircraft, what you see here. So these are the two regular gas turbines. So this one and this one. Yeah, and the third one at the back, what you see here is an electrically driven fan, and the electricity required to drive this fan is actually coming from a generator, which is actually also driven by this engine as well. Okay, and now there are some advantages of putting in a fan here. This is what is called as the boundary layer ingestion. Okay. If you want to have some more details, then I have given the link of the project here. Um, Now we are also looking again along with Airbus as well as NLR, which is the Dutch aerospace laboratories. We are looking at hybrid electric aircraft for single aisle aircraft. Yeah, and here are some of the concepts. What you see is what we call as a distributed propulsion. So there are several. So these gas turbines, they generate only electricity, and then it is distributed to over a large number of propulsors here, as well as to some big electric motors at the back. And what you see is that there is no tail here. This is a tailless aircraft. In fact, all the stability characteristics required to control this aircraft is coming from these two ducted fans. Yeah, and they have thrust vector control at the back. Um, and this is being done by one of my colleagues, Professor Leo Feldhaus. Yeah, and while we are looking to exploit synergies between how we can sort of integrate distributed propulsion system with aircraft aerodynamics and aircraft design in general. Okay, so here also you see that we are looking at hybrid electric propulsion, so this kerosene as well as electric propulsion. Now this is an example of a project that we did along with Pratt & Whitney and NTU and Airbus, and also by European Commission a few years back. And so this project has already ended in 2015. So I was heading this project where we were looking into the future of aviation and asking how are people going to fly in 2050. Okay, um, so we looked at the applicability of cryogenic fuels like LNG, liquefied natural gas, and liquid hydrogen, as well as biofuels in aviation. Yeah, so you see this what is called as a blended wing body aircraft. It had two engines, and these two engines, what we call as hybrid engines, because they use two energy source. I'll show you a schematic in a while, and it uses canards as a stabilizing surface, yeah, as a controlling surface. Yeah. So here you see the schematic of this aircraft. So the the yellow one is the passenger section. These are the tanks to store LNG, and these the blue one, what you see here, is the biofuel. Okay. So one of the things highlights of this project was we designed a different kind of engine, so it had two combustion chambers. So the first combustion chamber was in between the compressor and the turbine, like what I showed you in a normal turbojet. But it also had a second combustion chamber, and this toroidal second combustion chamber between the high pressure turbine and the low pressure turbine. Okay, so which means that the first combustion chamber could use LNG or methane or hydrogen, whereas the second combustion chamber could use biofuels. Yeah. So this was what was called as a hybrid engine, and it had several advantages, and we proved that by using such a architecture, such a novel engine as well as aircraft architecture, we could reduce the fuel consumption for a long-range mission as compared to a 777 aircraft, Boeing 777. So this dark blue one that you see here is a Boeing 777, and the light blue one is the aircraft that was designed by us. And what you see is that we could reduce CO2 emission by approximately 50%, and we could reduce NOx emission by approximately around 85 to 90%. This is an example of a very new latest project that we started just a couple of weeks back, also with Airbus as well as with Safran, where we are looking at using also hydrogen along with kerosene in aviation. This is supposed to be for the next generation of A320 Neo that will come in around 2035. Yes, so with that, I would like to close my presentation. Of course, if you have any questions, then please feel free to ask. Thank you.
Thank you, sir.
You're welcome.
If anybody has question, please ask the questions. Now, one question from my side.
Yes.
Now, you have shown one slide that during climbing, every time atmospheric conditions are not constant.
Yes.
So how the engine take that particular load and adjust the power during climbing?
Yeah. So that's a very good question, actually, because at takeoff you have a temperature of, let's say, around 30 degrees and an atmospheric pressure of 1.01 bars. But when you are climbing, of course, the altitude is changing, so the pressure is reducing and the temperature is also reducing. Yeah. But that is not a problem, actually, in the sense that the engine is designed for that. Okay, so the inlet conditions are changing, but and of course the velocity of the aircraft is also changing. Yeah, but the inlet is designed so that it provides the sufficient mass flow rate at all conditions, and the compressor and the fan are also designed to work on different operating conditions. Okay, so yeah, so the aircraft engine is designed for that. The turbo machinery especially is designed for this.
Okay. So can you elaborate that how different forces is balanced so that we get the resultant force that will climb the aircraft?
Okay. I don't have a schematic at the moment to show that, but you see that I mean during a climb, let's say first we have to look at what happens in a um, in cruise, let's say, okay, and then we can discuss what would happen in climb. Yeah, let me see if I can pull out. Just give me 1 second. Do you see a slide?
Yes, yes.
Okay, so this is again. So let's see what happens in during cruise condition. So this is an equilibrium condition, right? So in equilibrium condition, of course, you have the weight of the aircraft. Okay. Now this weight of the aircraft has to be balanced by the lift that is generated by the wings.
Yes.
And so the wing is the lifting surface. Okay.
Yes.
Now in the process of creating this lift, it also creates drag. Okay. So and so this is the let's say the resultant of the drag, and this drag has to be then balanced by the thrust. Okay. Now what happens, of course, is during climb there are a couple of more things. First of all, is that the aircraft is also accelerating.
Yes.
So that power has to be so you require energy to accelerate. So that means that energy has to be provided by the thrust. Okay.
Yes.
Secondly, is that let's say during cruise the angle of attack is not so much, so it's more or less horizontal, like what is shown here. But in climb, it is also climbing, so you have a gradient. So of course, then you have to take the components of the weight and the lift in the respective directions.
Okay.
Yeah, that means a large part of the lift. So because the wings are like this, so a large part of the you have to so the lift is like more or less like this. So you have one vertical component and then the horizontal component as well, and that horizontal component is actually then is sort of the drag.
Okay.
Okay. So these things you have to take into account.
Thank you. Thank you.
Welcome.
Anybody has some question? Tete sir?